Hi, Stuart here. Today we're going to talk about DevOps and containers as a mechanism that naturally goes together. And we're going to talk about it in the abstract in terms of how a design would work. I wanted to put a stake in the ground that there are already a number of open source projects and commercial projects that kind of work using this mechanism to one degree or another. But it's good to think about this in the abstract. And in fact, we've built this out of completely open source tooling to build a very practical container system to support DevOps and app development in general. So let's talk about some specifics. So we want to use containers, and by containers, for these sorts of projects, I mean Kubernetes. Although you could technically, I suppose, do it with Cloud Foundry, it's in some ways a little easier to do it with Kubernetes because it's less prescriptive and you can tune some of the components to suit yourself. So we want to have continuous integration builds. That is, we want, as people check in source code, we want to trigger a build engine and have it execute. We want to be able to do continuous deployment as appropriate. Generally, we do continuous deployment to the dev environment automatically, and then we have on-demand deployments to QA, UAT, and so on. And we want to be able to maintain all of our infrastructure as code through a central engine. And we want most of our code to run in containers, with the exception of storage and databases and things like that we'll use infrastructure as code if we have to, but ideally platform as a service or software as a service. And we want one fundamental tech stack, in this case Kubernetes, to provide all the functions. And we want everything in the entire system, including the build engine and the running applications and all of the supporting infrastructure and dependencies, to share one monitoring, logging, and awareness, MLA, and to have that all visible via one pane of glass. And then we want to be able to roll up costs by business unit and ecosystem. I'll touch upon that briefly. And we want stability and predictability. And I think at this point, the rubric is that Kubernetes and a lot of these other open source components are absolutely stable. Now, obviously, you don't have to use the open source versions of these. If you would like a throat to choke, so to speak, you can go ahead and get the commercial versions of these, and it'll work just as well. And you can have some curation and some support and things like that. This is all good things. But I'm just pointing out that we can do this on open source. So we have to define what an instance of Kubernetes is. So an instance is a isolated backplane, a share nothing backplane with other backplanes. That is, the backbone of Kubernetes is a whole collection of components that together form Kubernetes. And then its agent cluster. So the agent cluster is a whole bunch of VMs upon which the backplane can assign containers to run in pods. And it can expose services and all those good Kubernetes things. I'm going to sort of assume that people know at least the basics of Kubernetes as we go through this. And so why would you provision different instances instead of building one Uber instance of Kubernetes? Well, you might want to have one that is just the build plane, the build engine. So just the things we're going to talk about. You might want to have one that's a non-prod version of that same environment where development of the build agent pipeline happens separately from our production one, which, development and infrastructure teams count on to be up and reliable. And so we don't want to do our experimenting in there. So we probably do want to have a separate non-prod instance of the build engine itself. And we want to be able to support CI/CD and agent builds, IaC builds. And we probably want to separate prod and non-prod environments. And when we do a major upgrade, we probably want to bring up a parallel instance, do the upgrade, install the various components that run the entire system on it and test it, and then go ahead and transfer our workloads to it and then deprecate the old one. In other words, we don't want to do in-place upgrades as a general infrastructure as code practice, right? We want to do side-by-side or blue-green deployments so that we're never at risk that an upgrade or a patch or a change will nail our production infrastructure. Sort of the first place that it starts is we're going to create dynamically Docker containers with tools installed on them to do specific jobs. And the first specific job that we have to do is handle the case where someone has made a change to a Docker file or added a new Docker file, and they've asked that to be written to the Docker container registry so that it can be used to do other builds. So in other words, we need a bootstrap build that takes a Docker file and turns it into a Docker image that can be deployed by Kubernetes into a pod and scheduled and all those good things. In order to do that, we introduce our first idea, which is the scheduler. And this scheduler is separate from the Kubernetes scheduler. This scheduler specifically knows how to do two things. One is look for events from our Git ecosystem. And this can be GitHub, Bitbucket, whatever. And on the basis of those, it goes and it gets its metadata and decides what parameters need to get passed to a specific Docker image pulled from the Docker container registry. And those parameters will probably be set as environment variables or as files copied to the Docker image while it is being provisioned, etc. And then it will say, this is the set of instructions. It'll put those on a queue. And in fact, eventually that job will be handed over to Kubernetes itself to stand up the container in a pod and grant it the appropriate permissions and run it. And then in this case, the output of that build process is going to be another Docker image, which will go into the Docker container registry. And for all these processes, they'll leverage the horizontal green common backplane, which includes logging, monitoring, and alerting. So the whole system, including the output of all the build and script execution, goes into the single source of truth. And you can pick whatever logging, monitoring, and alerting framework you like. So if you like the ELK stack, you can use that. If you prefer using something else, you can use that, but it's important to have one. Likewise, all of this is dependent on there being identity and access management. And again, in Kubernetes, there's lots of pluggable choices. We need cryptography and other shared services. And of course, we need the network building blocks upon which Kubernetes will create load balancers and things like that. And then obviously we need disk storage and we need an artifact repository, and we'll talk more about that. But in this case, the source and the sink of our agent build pipeline is the Docker container registry. In other words, we pull an image that knows how to build Docker images and send them to the container registry and use it to transform our Docker file from our Git environment and write it back to the Docker container registry as a new version of that image that will then be used for other nefarious purposes. So that's kind of the bootstrapping cycle. And obviously, the very first time we stand up the system, the first thing that we have to do to seed the systems to support all the job types is manually create the Docker image creator and push it to the DCR and manually create the scheduler metadata that goes with it so that, and the script which the scheduler will execute in association with this event, that there is a new Docker container that needs to be turned into an image. And after we've bootstrapped the kernel of that system, then that same mechanism now is available to use for doing all of our other builds. So it's very much by its bootstraps sort of a thing, starting from essentially plain Jane Kubernetes instance. So then that brings us to infrastructure as code builds. You can use whatever infrastructure as code engine you like. Terraform, Ansible, Azure Control Language, almost any desired state configuration engine will do. And in fact, as long as you have the appropriate APIs and deployment engines as part of your cloud infrastructure, especially if you're running in Azure, AWS, or Google, there's plenty of pre-installed things to run. And the idea is that, again, we trigger a job that awakens the scheduler who looks at the job metadata that was used to trigger it, decides what script to execute, and pulls whatever Docker container images are required out of the registry and any metadata, and spins up a Docker container in a pod via Kubernetes, and it executes and attempts to create the appropriate infrastructure, and that can be K8s itself, right? So we could actually use this process to boot up or provision a new Kubernetes instance. In other words, we could bring up a backplane and a set of agents using this mechanism. We could use it to provision PaaS offerings that are in our cloud, or to ensorcel SaaS offerings that are available. But essentially, the components are the same as our bootstrapping components, except this time when our Docker container image runs, it's going to be issuing commands against the cloud API, the IaC engine API, and so on. So if it's Ansible, it will be sending commands to the Ansible controller that lives up in our cloud infrastructure. And the Ansible controller will play Ansible playbooks, and those playbooks will create and configure our infrastructure. And again, the output of this process leans on the things in our basic common backplane stack, which may or may not be implemented partially in Kubernetes itself. It's all very meta. So a typical developer build would be that a developer has some code, and they do a pull request to their peers, which gets reviewed and approved. And that, again, triggers the scheduler to execute with a particular set of metadata. And then it pulls information about what it should do, including what Docker image to fire up, and creates a Docker image with, what Git repo at what change set it needs to build. And each Docker container image would have a slightly different tool chain for each need. So based on the scheduler that's triggered, it would pull the appropriate Docker image from the Docker container registry and use that to actually do our build. And the difference between that and building Docker images itself is that the output of a successful CI build is that we actually write the compiled or assembled or organized code into an artifact repository, typically as some sort of compressed file, a tar, a zip, whatever. And we add metadata to it, like the change set number that went with it and who triggered the build and all the other metadata that we might care about. And it lives in the artifact repository as the output. And again, our green stack does a lot of heavy lifting for us. And so at this point, we have artifacts in our artifact repository that could be deployed. And so something will trigger the scheduler. The scheduler will say, I need to run this scheduling script. The scheduling script will say, well, I need to pull the Kubernetes deployment script for Python out of my Docker container registry, or for .NET Core or Java or whatever. And the reason for that is because then it will know when it pulls the artifacts out of the artifact repository and unpacks them, what commands it needs to execute in order to get the code successfully deployed and configured in our target, which in this case is another instance of Kubernetes. But it could be VMs, it could be whatever. we're trying to be very meta about this system. And so we're deploying to Kubernetes for the most part. So that's how that works, right? And again, you can see a theme going on here. So if we take a look at the builder internals, that is the things in the rightmost box, what we're seeing is that there's a common pattern here. We have a UI, a website typically that we use to interact with the system and configure it. So we would say if this Git source code repository on this branch has a merge, then I want you to take that information and go look up the script in the build state storage. And then I want you to call the build API and pass it and the other metadata that came to it to the scheduler. And the scheduler will go and take all that metadata and put it into a standard format and put it into a queue. And then the job executor will work with Kubernetes to turn that into a container or containers running in pod or pods. And we'll use the job metadata provider to see the images that are deployed to do our unit of work with the metadata they need to succeed. And then Kubernetes will then bring up the pod and the instances, and they will run and do their work and write to the MLA engine, the logging engine. And then when they conclude, their exit code will be used to determine whether or not they've succeeded or failed. And then the results of that go back into the job queue and are acted on by the scheduler. And in fact, you can use that to chain together. So you can say, well, on a successful CI build, I want it to then run a security scan. The security scan may take a really long time to run. So out of bands, asynchronous, I want the security scan to run. Or I want it to run a notification job that says, oh, well, I want you to tell a bunch of people in a bunch of different ways that there's this new version of this thing that could be deployed or whatever, right? So the pattern is that the scheduler writes things to the job queue. The job executor takes things off the queue, and based on the instruction in the message in the queue message, it does different things. So it can invoke the Kubernetes API to bring up running images. It can call the scheduler and execute downstream steps. These can be done in parallel even, and so on and so forth. And the execution flow is entirely flexible. You can decide what you want to do. And the so-called dynamic agents, therefore, are just Kubernetes building a pod and deploying instances to it. And those instances run until they stop or error. And then you make a determination based on what happened about what happens next. And so one of the things the scheduler can do, for example, is the job executor can see the results of a dynamic agent coming to an end and schedule one of several kinds of messages into the job queue. And then based on whether it's successful or failure, the scheduler might invoke different kinds of messaging. So there's the top level design idea behind using containers to support DevOps. And we'll break this down more in future videos.